We are now engaged in the calculation of a shprengel truss. Create a new task. We enter the graphic editor. Set the required grid spacing. Draw the outline of the future truss. We divide the upper chord into 8 parts. Set the flag node on the line and cut the node into the lower chord. Draw the remaining filling of the scheme. Enter the operation mode and reflect the drawn part relative to the plane x equals 6. Go to the Elements mode and attach the sections to the lines of the skeleton. Chords, braces and vertical web members are created as beam elements. If we want the program to generate stresses at certain points of the section, we need to fix these points on the section image. At the ends of the braces we introduce hinges. Elements of subdivided panels will be created as links. For links by default, hinge attachment is assumed. You can see how the sections are set. We switch to the links mode and impose external restraints. We impose restraints from the plane of the truss onto the upper chord, as if simulating the presence of stringers. We set the static loading. We will have a single load, a distributed load along the upper chord of the truss. Set the material and bind the finite elements to the selected material. The analytical model is ready. We return to the control section and perform a static analysis and a calculation for overall stability. Set the relative accuracy of the search of the critical parameter, and set the calculated combination of loadings. Enter the mode of viewing the results of calculation. Open the static analysis. We're in the reference mode. You can see the displacements of individual nodes, strengths in the elements, support reactions, see moment diagrams. Show stress distribution. Minimum stresses. Maximum stresses. Real stress distribution. You can examine in detail the stresses on a single element. To the buckling mode. The safety factor for buckling 1.086. A byproduct of the buckling analysis is flexibility and buckling lengths of beam elements. Unfortunately, this data is not always possible to use, as can be seen. For the elements of the upper chord, the coefficients of the buckling length when bent from the plane of the truss are more or less likely in the plane too high. For bracing, the values of the coefficient mu are too high. More or less reliable values the analysis gives only for those elements that are really responsible for the loss of stability. For most of the elements, these results cannot be applied to assess the local stability of the rods. We will now perform a calculation that allows you to check the local buckling of the core elements without invoking the concept of the buckling length. Returning to the control section, select the calculation of buckling beam members. Since we will further have the opportunity to perform this check according to the norms of SNP February 23, 81, so that we can compare the results, we choose SNP February 23, 81. The reason for the premature loss of stability of core elements is the presence of small initial imperfections in them, in other words, curvature. Due to this, even with the central compression of such rods, a moment stress state arises in them. And, if the total stress in one of the core fibers from the longitudinal compression and from bending reaches the limit value, then the rod already after this cannot bear the load. This regime just provides the calculation with slightly curved rods, in accordance with the selected norms. The program randomly distributes the depths of irregularities between the core elements and makes several recalculations of the structure according to AP delta analysis, changing the distribution each time. After this, having statistically processed the results, the program concludes, can the fiber stresses in each of the elements exceed the design resistance? The limiting error of determining the stress state of each of the calculations is set as the initial data. To avoid cycling, the maximum number of iterations, the number of recalculations, that is, the number of samples. The way of coupling of structural elements is established. The first option is to bend the rods by installation to a straight line. The second option is to include him in the construction in their natural state. The first option corresponds to the connection on the bolts, the second, to the welded connections. The flag conjugate adjacent sections make sense to include if you have for some purpose previously divided some rods into continuous chains of segments. For the rest of the parameters, you can ignore them. The program makes several recalculations. Entering the results viewer. Choosing beam buckling. Go to the beam stresses mode. Mark all items. And click on the button 99.9. The program shows the values of fiber stress, which with a probability of 99.9% will not be exceeded. An even clearer picture is obtained by clicking on the sigma divide by R button. As a result, we immediately see elements that are in the danger zone for the elements of the upper chord. Painted blue, the fiber stress is almost equal to the design resistance. Let's return to the control section and do another calculation, determination of buckling lengths. We will need his results to check the cross-sections. We enter into the viewing results. Go to the buckling lengths. Click in the Mu button shows the values of the coefficients of the buckling length of each bar when bending with respect to both main axes of the section, upper, relative to the local y-axis, lower, relative to the z-axis. Clicking on an element gives more complete information. As you can see, there are no huge buckling lengths. Moreover, the buckling lengths are calculated even for stretched elements. The buckling length of the rod is determined by the geometric characteristics of the section and the conditions of its attachment. The secret of this analysis is that the program for each rod finds a reaction from the rest of the structure at its attachment points. And it does it absolutely accurately and very quickly. This allows you to set the true value of the buckling length of each rod element. We now turn to the verification and selection of sections. But before that we need to find the most unfavorable load combinations. Actually, we have the only loading. But still we need to go through the procedure of combinations. To do this, we need to create a graph of combinations. Entering the text editor. Choosing a table graph of combinations. Note, this is the only table that is not supported by the graphical editor. Our graph looks very simple. For more information about the formation of graphs of combinations can be found in the instructions. Entering the combination mode. We form combinations orders. To calculate combinations, it is enough to go to the results of combination mode. We will not dwell on combinations, but immediately proceed to the verification of sections. Setting the task parameters. Mark all the elements of the scheme and activate the panel of group setting parameters. Set the buckling length when bending relative to the local y-axis. The estimated lengths can be set according to one of the standard calculation schemes, or according to the results of the analysis for stability, or according to the results of the calculation to determine the buckling lengths, or entered manually. We choose, according to the results of the calculation to determine the buckling lengths. Do the same for bending about the z-axis. Mark the chords and assign them to the chords. Bracing refers to the holding diagonals. Vertical posts to the supports. Shprengel elements to last link elements. Checking cross-sections. Elements that went through all checks are colored in green. Red. Elements that are not passed. Clicking the right mouse button on the element gives reference. Each check is preceded by a number. By pressing the F1 key you can see what each check means. Following the number, the resource is printed out, that is, the ratio of the calculated value from this check to the limit value. As in the case of calculation that taking into account the initial imperfections, the program points to the elements of the upper chord. We will ask the program to select the optimal sections for non-passing elements. Mark non-passing items and launch dimensioning. The program has found the nearest passing section. Dimensioning is always carried out within the same assortment as the original section. Now we have to do the final step, reassign the non-pass sections and repeat all the calculations. We, of course, in an amicable way, would have to reassign the entire top chord. But we will specifically reassign only the non-passed elements to make sure that the program will correctly form a new stiffness group and correctly redistribute the elements on the orders of the combinations. Mark the elements to be reassigned and select the Insert into Design mode. Back in the graphic editor, the program warns that since the sections have been reassigned, it is necessary to repeat all the calculations. We see that the program has created a new stiffness group. Repeat all analysis. New order in the combinations. As can be seen in one iteration, it was not possible to bring the design to a satisfactory state. Apparently, This is due to the fact that with an increase in the cross-sections of previously non-passing elements, their buckling length also increased. But by repeating the same procedure, one can eventually achieve a satisfactory solution. That's all.